So let's begin where we've now gotten to the citric acid cycle, which we're going to do all of it today. Most of it will be chemical steps that you have seen before. The goal in the citric acid cycle, if you remember our starting point, is going to be to convert acetyl-CoA into 2 molecules of CO2. And I'm going to make this balanced. We're going to say, remember, we started with glucose, and we generated 2 molecules of pyruvate from glucose in glycolysis. Then we converted those 2 molecules of pyruvate to 2 molecules of acetyl-CoA in the pyruvate dehydrogenase complex. And now in the citric acid cycle, or the Krebs cycle, we're going to convert 2 molecules of acetyl-CoA into 4 molecules of CO2. And along the way, we're going to recover a bunch of molecules of NADH and ATP. And you'll see just how much we generate along the way. We'll summarize this in the end. We'll make, let's see, I'll just write it down here as part of the overview. We're going to make 6 molecules of NADH, 2 molecules of FADH2 for every 2 molecules of acetyl-CoA that we bring into the process. And then we will also make 2 molecules of GTP. And you'll see later on that we can exchange GTP easily for ATP, that at the rate of about 1.5 ATP per molecule of FADH2, we can get something like 3 molecules of ATP out of FADH2. And then at the rate of about 2 molecules of ATP, and you'll see this number sort of, this yield of ATP per NADH. The number is based on various assumptions and it changes. You'll hear anywhere in the range from 2 to 3. We'll go with the more conservative estimate, about 2 molecules of ATP for every molecule of NADH. You get an idea of all that we make in this process from acetyl-CoA. And we'll summarize that later. This isn't really anything to memorize in terms of numbers other than to try to get an overall sense for what's going on in the process. And it seems like maybe I've made a mistake, but I think that's basically close. No? What did I do wrong? I was hearing muttering, so I figured I'd done something wrong. Just self-conscious. People expect more of you when you wear a tie. Okay, so we'll check those numbers a little bit later. Actually, I have them here. There we go. Okay, it's 2.5 is the number, I guess. I knew that sounded low. It's about 2.5 ATP. So that comes out to about 15 ATP from the NADH. Let me check my notes there. 5, yeah, pretty close. Okay, we're good. So overall, from the citric acid cycle portion, if you sort of add things up, we're getting about 20 molecules of ATP out of these 2 molecules of acetyl-CoA. You tack that onto what we earned from glycolysis and the pyruvate dehydrogenase complex, and you can calculate exactly how much ATP in general you can get per molecule of glucose. And we'll say something about that at the end. So let's just draw CO2 briefly, because you need to have a real feel for what's got to be accomplished here. Notice the 2 carbons that we've got in acetyl-CoA. You've got the carbonyl carbon and you've got the methyl group. The carbonyl carbon is not too far from a CO2 oxidation state. We've got 3 bonds to a heteroatom, so we've got to oxidize that one more time to make CO2. However, the blue carbon is a methyl group. It's got 1 other bond to carbon. That's not oxidized very much at all. So we've got a lot of chemistry to do. And the beauty of the citric acid cycle is going to be to oxidize carbons all the way up to CO2, to lose CO2 by decarboxylation. And then once we're done with that, the goal is to get back to the same place that we started so we can make a full cycle. If you want to lose CO2, you guys now know 2 biochemical strategies for that. One of that is to decarboxylate a beta keto acid, and that happens spontaneously. You can also do, so that's method 1, you can also do oxidative decarboxylation of alpha keto acids. We learned how to do that last time, and that was using something like the pyruvate dehydrogenase complex with TPP or thiamine pyrophosphate and lipoate as cofactors along with NADH. So along the way of the citric acid cycle, be looking for chances to make a beta keto acid or make an alpha keto acid. Those are the steps where if you can get to that point, then we can lose CO2. All right, so try to have a sense for the general chemical logic of this. Step 1 of the citric acid cycle involves one equivalent of acetyl-CoA and then a ketone starting material that's called oxaloacetate. So oxaloacetate is a 4-carbon molecule. It's got carboxylic acids on carbons 1 and 4. And then on carbon 2, it's got a ketone. So this is oxaloacetate. And I'm going to want you to know the names of these intermediates in the citric acid cycle. The reaction is catalyzed by something called citrate synthase or synthesis innator. This is the enzyme that synthesizes citrate. And what does citrate look like? Here are the 4 carbons that were present in oxaloacetate. Here's an OH group, and then here's 2 new carbons, and this is called citrate or citric acid. Here, for now, we'll just label the 4 carbons from oxaloacetate and the 2 carbons from acetyl-CoA, and that's citrate. The reaction mechanism is basically twofold. First, there's an aldol reaction. So the acetyl-CoA enolate attacks the ketone at the carbonyl carbon. I will show you just briefly, I'm going to show you snapshots of the mechanisms. I would expect you to be able to push arrows through all of them, but I'm not going to spend time showing you how to make an enolate from acetyl-CoA because I'm assuming at this late stage of the class you already know how to do that. If that's not the case, please come talk to me and we'll work through it. Here's the acetyl-CoA enolate with a negatively charged alpha carbon. It's going to attack, oops, arrow went too crazy, going to attack the carbonyl carbon to get a tetrahedral intermediate. That's the aldol step. I'll draw real briefly the intermediate that would be present after that aldol step. I'm going forward, I'm protonating the tetrahedral intermediate on the carbonyl, on what used to be the carbonyl oxygen. That's why I've used sort of 2 arrows here. Here is the new bond we made in the aldol reaction. Here are the 2 carbons from acetyl-CoA, and there we go. Okay, that's the aldol reaction. Then to get from there to the citrate product, we need a couple of, yeah, what's wrong? Can you say that again, what?
Are you attacking the correct carbonate?
No. Thank you. I knew the arrow was headed in the right direction in the first place. There we go. Yes, that was bad. I was in a hurry and didn't notice what I was doing. Of course, you would never attack the carbonyl carbon of a carboxylate because it's not an electrophile. It's got a negative charge on it. Is everybody okay with that? We attack the ketone, which you know is the most reactive portion of the molecule. Thank you, and I'm sorry. Again, you expect better from people in ties. Maybe I should take it off and your expectations will be a little bit lower. All right, so the first reaction is the aldol. Okay, and the second, which I'm also not going to draw for you because I think you can do this, is thioester hydrolysis. Briefly, you would need to deprotonate water so hydroxide could attack the carbonyl carbon of the thioester to get a tetrahedral intermediate, and then the negatively charged oxygen would kick off the negatively charged coenzyme A thiolate as a leaving group. I'll put that there in parentheses. You should still go through that and make sure you can do that. That is a nice review of the stuff we did during the first exam, the thioester hydrolysis. The aldol reaction, if you want to push arrows through that, that is a nice review of stuff we did for the second exam. Okay? That would be worth doing, though we won't do so in a lot of detail here. Okay, questions about that? Yes?
On step one, how do you make it so that the oxaloacetate doesn't get the hydrogen removed? Like, wouldn't that hydrogen be more acidic?
Yeah, so the question is, you have, you've noticed, great noticing actually, that's good, that's, you've noticed here that there is a proton that is alpha to 2 carbonyls. Wouldn't that be more acidic? And the answer is yes, absolutely. Why is it that nature selectively deprotonates the thioester? I don't know. It's possible that nature and I'm speculating here, but it would be the shape of the active site that would put the base in the presence very close to this alpha carbon and not very close to that one. It's not a great answer, but that's all sort of I have. And there may be more details that you'll learn in biochemistry. Good. Others? Okay. One thing I want you to notice is that in an aldol reaction, if we made a stereocenter, we would expect both configurations. If we did that in solution, an enzyme can control stereochemical configuration. It doesn't end up mattering here because, is that a stereocenter? No. In fact, citrate is symmetrical. That's what I'm trying to say. Notice that this chain here, these 2 carbons with a carboxylate, is identical to that one. It is at this stage where we completely lose track of the 2 carbons that we brought in acetyl-CoA. You will want to go through the citric acid cycle and follow each carbon from acetyl-CoA and see when it comes off. And actually, it probably takes multiple turns of a citric acid cycle for both of the carbons from one particular acetyl-CoA to come off as CO2. But doing that is kind of pointless because we lose track at this stage of which one is which. You can't tell anymore. Okay? So don't worry about it. Remember, our task as we turn through the citric acid cycle is to lose 2 CO2s. Our strategy for that will be to make a beta keto ester or a beta keto acid or an alpha keto acid. Then once we're done with that, we need to get right back to where we were in the starting material, this oxaloacetate. Okay? Good. So let's now do the next step. Some people, in terms of how you talk about steps in the citric acid cycle, some people talk about reactions and others talk about enzymes. The reason that matters is that sometimes there are individual enzymes that catalyze the same step, and that's an example of that is what I'm going to show here. So I'm going to call this steps 2 and 3 because it's all catalyzed by the same enzyme, and that enzyme is called aconitase. So we need to start with citrate, and again, the structure of citrate is you've got 1, 2, 3, 4 carbons with carboxylic acids on either side. You've got an OH group here, and then you've got another acid here. If you look at the structure of citrate, it's a problem because we can't currently with citrate make an alpha or a beta keto acid. One strategy for taking a molecule like citrate and doing that would be to oxidize that OH group to a ketone. Why can't I oxidize the OH group in citrate? Tertiary alcohol, there's no hydride to lose, right? So we need to move that OH group. And our strategy for removing that OH group is going to be to do what we often do after an aldol reaction, which is E1CB style dehydration. Remember, in an E1CB reaction, we remove a proton that is alpha to a carbonyl carbon to generate an intermediate, an enolate. So there go the arrows onto that alpha carbon. I'll draw that intermediate for you. And then electrons kick down and OH minus leaves as a leaving group. That's the dehydration step that frequently followed an aldol reaction. And the product that's formed after that is an alpha beta unsaturated carbonyl compound. Okay, let's count the carbons. 1, 2, 3, 4 that were in the backbone, and 2 that here that came from acetyl-CoA. 1, 2, 3, 1, 2, 3, 4, 2, 1, 2, 3, 4, 1, 2. The double bond is here, and this intermediate is called cis aconitate. And that is the alpha beta unsaturated carbonyl compound that is a product of this dehydration step. Okay? Now, our goal was to move the OH group over. One of the beautiful things about cis aconitate is it's alpha beta unsaturated in multiple directions. So let me illustrate that. If we let this be the blue carbonyl carbon, that's the blue alpha carbon, and that's the blue beta carbon. In pink, let's let this be the carbonyl carbon. This is the pink alpha carbon, and this is the pink beta carbon. That double bond is alpha beta to 2 carbonyl carbons. So now the OH group that left can do one of 2 possible things. It could come back in and attack at the pink beta carbon, or it could come back in and attack at the blue beta carbon. If it attacks at the blue beta carbon, that's the backward step to that E1CB style dehydration. That takes us right back to citrate. That happens. The enzyme catalyzes that backward step. In contrast, if hydroxide attacks the pink beta carbon via a conjugate addition step, then we're going to generate the following intermediate that looks like this, with a negative charge on the pink alpha carbon. And the OH group is going to be here on, I gotta get the stereochemistry right. It's going to be here on the pink beta carbon. Okay? And then, of course, that enolate will pick up a proton from some source. We don't care where, probably the enzyme. And that will generate the following intermediate. It is an isomer of citrate. And the stereochemistry is known, but it's inconsequential. So I'm going to draw it, but it doesn't end up mattering for our purposes. You get this molecule here, which is called, as an isomer of citrate, it's called isocitrate. Again, follow the carbons. You've got 1, 2, 3, 4 in the main chain, 1, 2, 3, 4, 2 in the side chain. All we've done is we've moved the OH group, which I'm going to highlight in green, from here to here. and created 2 stereocenters. All right? Can you get a glimpse of what nature is trying to do? You move the OH over, now it's at a secondary carbon. That's oxidizable. And look at that secondary carbon. It is, again, this is the pink carbonyl carbon, pink alpha carbon, pink beta carbon. That OH group is beta to the pink carbonyl carbon and is alpha to the blue one. I told you before we wanted to make this process work by decarboxylation of either a beta keto acid or an alpha keto acid. We're almost there, folks. All we got to do is oxidize the OH group to a ketone, and then we got both. Okay? Questions about that? Yes?
On the beta carbon, why did the OH switch stereochemical configuration?
Because I wasn't paying attention. Sorry, that's a dumb answer to a good question. Why did the OH switch configuration? It should not have done. That was just me not looking at my notes carefully enough. Thank you for that. Yep.
Is it because you rotated it to the end of the page? Because now the top carboxylate is out of the page.
The top carboxylate is out of the page to reflect the fact that once you protonate at this pink alpha carbon, it's now a stereocenter.
Okay.
Yeah. Whereas that alpha carbon wasn't a stereocenter before.
Can it exist in both stereo?
No, you get specifically this isomer. Yes. Others, yeah, same question. Yeah. And one thing you should understand about enzymes is that a lot of processes that if we did in the lab without an enzyme would result in a racemic mixture of enantiomers or both stereochemical configurations. In an enzyme, it's not such a big deal. Protonating this enolate from the bottom face happens presumably because the enzyme blocks the top face. So you see in isocitrate how that proton got added from below. You might ask, why doesn't it get added from above? Well, because the enzyme holds on to it in a certain way that only allows the proton to be donated from below. Does that make sense? Okay, good. All right, so the next, again, we're going to group the next few steps, the next 2 steps, because they're catalyzed by the same enzyme, though we will identify and name the intermediate. I'm not necessarily sure whether my numbering of these steps is identical to the numbering of steps that's included in your text. That's okay. The chemistry's all the same. It's just in terms of how you count. So, isocitrate we'll draw here. Again, this carbon will be a wedge. Then there's the main chain 2, 3, 4 with a carboxylate here. And then, make sure we got it right, here's the OH group and the other carboxylate. And again, for fun and monitoring things, we'll continue to label the pink and the blue carbonyl carbons. This is isocitrate. The enzyme that catalyzes this process is called isocitrate dehydrogenase, which tells you that it's going to do what? Oxidation chemistry. And if you were going to guess which, where, and what is going to get oxidized, what would you say? It's that alcohol, right? Because strategically that makes sense, right? We're gonna generate a beta keto acid and a beta keto and an alpha keto acid in the same step. So this is going to follow the basic same mechanism that we have used many times previously for NADH or NAD plus mediated oxidations. A base will remove the proton from the alcohol, electrons will kick down, and hydride will get delivered to the paracarbon of NADH or NAD plus to give as products, or as an intermediate, let's see, you get NADH, and then we can draw that intermediate. Some people consider this one of the products or one of the steps of glycolysis, but it turns out that, and that's fine, we'll go ahead and draw it. We need to draw it because it illustrates a key point. This is called oxalosuccinate. Okay. And it's now got the requisite ketone group, beta, to the pink carbonyl carbon. And you know that beta keto acids spontaneously decarboxylate. So this happens in the same enzyme active site. This is why some people, when drawing out the citric acid cycle, won't even bother to draw oxalosuccinate as an intermediate. They'll just show you skipping directly from isocitrate to what we're going to draw next, because they say, hey, the decarboxylation happens still in the enzyme active site. And that's true, but I think it's useful to draw out oxalosuccinate so you can see it for what it is, which is a beta keto acid. And beta keto acids can spontaneously decarboxylate because when they do, the electrons from the carbon-carbon bond that's going to break end up on a carbon that's alpha to a carbonyl, where they are stabilized by resonance. So electrons on this negatively charged carboxylate oxygen kick down to make a new carbon-oxygen pi bond. We're going to lose that carbon as CO2, okay? And then the electrons in this pink carbonyl carbon to pink alpha carbon bond, that bond breaks and the electrons move out onto the alpha carbon. So there is the CO2 that we lost. And that's, if you're keeping a list or keeping score of what needs to happen, check off that box. What's left is the following now 5-carbon intermediate. I'm going to continue drawing it in roughly the same orientation, at least just for this step, so that you can follow what's going on. Here's the ketone, here's the enolate, right? And now what's left is the blue carboxylate carbon and the alpha ketone group. And then, of course, the negative charge on is here, and it's alpha to this carbonyl carbon. So we'll now call this orange carbonyl carbon and this orange alpha carbon. Multiple carbonyls, multiple alpha carbons, hopefully you're okay with that. We've been using alpha and beta a long time to count distance from groups. The point is that this enolate is resonance stabilized, okay? And then it's going to get protonated on that alpha carbon with some acid to give us the product of this step, which I will now draw just as a linear carbon chain. It's a 5-carbon chain, 1, 2, 3, 4, and then a carboxylate on carbon 5. This is called alpha keto glutarate. Glutarate is a name for a 5-carbon dicarboxylic acid with carboxylates on either end, and then the alpha keto tells you everything else you need to know. You have a ketone on the blue alpha carbon. Okay? So far we haven't generated any ATP, though we did just generate 1 molecule of NADH. Okay? So we're highlighting that with an explosion because that's yield, that's power. We can generate ATP from that. That's payoff. All right. Good. Questions about that step? Okay. Well, we're not going to wait any longer for what happens to alpha ketoglutarate. I told you that you could do a decarboxylation of a beta keto acid and, check that one off. The next thing we can do is oxidative decarboxylation of an alpha keto acid. So that's going to be step, let's see, we need a new page. Sure, that'll work. That's going to be step 6. So step 6, we will not draw the mechanism out because it's going to follow in all essential details the same mechanism as we saw for the pyruvate dehydrogenase complex. In fact, the complex of enzymes that catalyzes this reaction is called the alpha ketoglutarate dehydrogenase complex. As with, as we saw before with the pyruvate dehydrogenase complex, this is going to depend on, this reaction is going to depend on TPP as an intermediate, thiamine pyrophosphate. It's also, as a cofactor, it's also going to depend on lipoate, which is this weird 5-membered ring containing disulfide molecule. So those are going to be cofactors. I'm drawing them here to remind you of them. Also, we saw before that this mechanism will take NAD plus and generate NADH. It's an oxidation mechanism. Again, we will not go through it in a lot of detail because you've basically seen it before. And then in addition to that, you need to bring in, let's see, coenzyme A as a thiol. And when that process is done, we're going to lose that as CO2. And what used to be blue alpha carbon is going to get oxidized to a thioester. And again, go back in your notes. We don't have time to talk about this in a lot of detail. But if you remember how we turned pyruvate into acetyl-CoA and CO2, that was all Monday's lecture. You'll be able to follow through what's happening with alpha ketoglutarate. It would be good for you to actually practice that based on what you saw in the pyruvate dehydrogenase complex to make sure you've got it. By the way, your text doesn't show you those details. That's uniquely what I told you, although it's available in any biochemistry text. It's on Wikipedia. If you Google it, you should see sufficient details to get through it. In the lecture notes from last time and in the video from last time are sufficient details to get you going on that. Okay, so the product there is CO2. So there we've lost our second molecule of CO2. What's left is the remaining 4 carbons. 1, 2, 3, 4. On this end is a carboxylate, and on this end is the coenzyme A thiol or thioester. And this intermediate is called succinyl-CoA. That succinate root describes a 4-carbon chain with carboxylates at carbons 1 and 4. It's also fun to say, succinate. Okay, succinyl-CoA, which is now a thioester. Okay, so in the first 6 steps, we have lost both molecules of CO2. We did that using time-tested strategies. We now need to zoom out once more and remind ourselves of where we started. And I'm going to just copy the oxaloacetate structure so you can get an idea of what still needs to happen, comparing the thioester above to the oxaloacetate, because in the remaining few steps, we got to complete the cycle. But notice what's got to happen. We got to hydrolyze the thioester to a carboxylate. That's boring. We know how to do that. That could happen spontaneously. But guess what? Biology doesn't like boring. Biology is actually going to use this thioester for something useful. We're going to generate GTP from this thioester. Because remember, thioesters are pretty high in energy, just below aldehydes and ketones and mixed anhydrides. So we're actually going to use that thioester to make a molecule of GTP. Then after that, we've got to oxidize the carbon, the carbon that's alpha to the thioester. We've got to oxidize that to a ketone, which is weird because right now it's just a CH2 group. But as we do those oxidation reactions, we're going to generate some NADHs and some FADH2s. Okay, so let's proceed onward. Other questions? Okay. So that's our goal at this point, to complete the cycle. Step 7 is going to be, we start with the succinyl-CoA thioester. Okay. And then nature's going to use a molecule of inorganic phosphate. What the heck does nature mean by inorganic phosphate? Most of your biochemistry text will abbreviate it as PI. They simply mean a phosphate group that's not attached to a carbon. This is just dissolved in your blood, and in the cytosol, it's just present, okay? Easily accessible. So nature's first gonna use, let's see, overall, the enzyme that does this is called succinyl-CoA synthetase. All right, it's actually named for the backwards reaction. But let me show you overall what happens. You're going to take GDP and inorganic phosphate combined to make GTP. Also, coenzyme A is going to be kicked off as a leaving group, and then you'll get this 1, 2, 3, 4 carbon succinate acid out as a product. The succinyl-CoA synthetase is named for the backwards reaction. Thinking backwards, what you would do is have the carboxylate attack the gamma phosphate group of GTP to generate a mixed phosphoanhydride. Then coenzyme A would come in as a nucleophile and do nucleophilic acyl substitution. The way the reverse reaction happens is like this. I'll show you maybe just part of it. Step 1 is phosphate attacks the thioester, nucleophile attacks carbonyl carbon. I'm going to call that step 1 is nucleophilic acyl substitution. I will draw the product, and then it would be worth you going back and doing a little bit of practice to make sure you can draw that mechanism. Here's the carbonyl carbon, here's the rest of the succinate molecule. On carbon 1, you now have the phosphate group. Okay? And because of pKa's at physiological pH, you'd be totally fine drawing either this form or the dianion on the phosphorus. Either one is reasonable. It doesn't matter for our purposes. Okay? Basically, attack the carbonyl carbon, make a tetrahedral intermediate, electrons kick down, thiolate leaves as a leaving group. Okay? So now you've converted the thioester into something that's also reactive. It is a mixed phosphoanhydride. Okay? That's going to be the gamma phosphate group. And then you're going to have the beta phosphate group of GDP, which we'll draw here. Here is the ribose ring, and we're just going to draw G. What's the difference between GDP and ADP? Just the identity of the base there. Does nature use them for different things? Yes, but they're sort of exchangeable. So we're going to consider this GTP as though it were an equivalent of ATP. Basically, what you're going to do here is the standard kinase type mechanism. Some of you would be more comfortable if this enzyme were named a kinase rather than a synthetase. I don't really care about the distinction, but that's what the enzyme's name is, so what are you going to do? We would draw, I'm not going to draw now, but we would draw a pentavalent intermediate where the phosphorus is bonded to 5 things, and then electrons would kick down, and everything here would be the leaving group. So again, this is basically step 2 is basically another nucleophilic, maybe not acyl, but phospho substitution. And that gives you GTP and succinate. Okay, so nature's not wasteful here. You could have just hydrolyzed the thioester, but nature's recovered something that's valuable. That's GTP. Questions about that? Okay, good. Let's keep going. We're only a couple of steps from the end. A couple, which means now 3, I guess. Sorry, couple stands means 2, but we're actually 3 steps from the end. But the remaining steps are pretty simple. Okay, so we're going to start in what I'm calling step 8 with succinate. That's the 4-carbon diacid. 1, 2, 3, 4. And the enzyme that catalyzes this reaction is called succinate dehydrogenase, which tells you that it's going to oxidize succinate by removing hydrogen from it. The enzyme, or let's see, the cofactor is FAD. This is different from NADH. In the sense that the structure is different. The product is going to have a pi bond between the alpha and the beta carbons of succinate. So there we go. And then on the other side is still the carboxylic acid. This product is called fumarate. And I don't know why it's called that, but I note the Spanish infinitive fumar, for to smoke, embedded in there. I don't know if it smells smoky or what. Somebody should look that up, but that's actually the name of it, fumarate. Okay, the mechanism is going to be essentially an E1CB mechanism. Succinate is symmetrical. You've got an alpha carbon that's identical to the beta carbon. So you're going to make an enolate first. It's going to be an E1CB style type mechanism. A base removes a proton from the alpha carbon. That generates your enolate intermediate, and then the enolate will kick off the adjacent hydride. Oops, there we go. I don't like where that negative charge is, sorry. Negatively charged alpha carbon electrons kick down to make the pi bond, and hydride gets delivered to FAD. Now, real briefly, FAD was kind of a complicated structure. You can go back and look at your notes because we talked about it in a lot of detail in a previous class period. I'm going to push the arrows here without a lot of explanation, and if you need more, you can go back to the previous class period where we talked about it. The hydride gets delivered to this nitrogen, arrows rearrange themselves, and the nitrogen on the bottom picks up a proton from some other source. That gives us both fumarate and FADH2 as products. Okay. So that's sort of unusual. You've never seen hydride. Hydride's almost never a leaving group unless it's handed off directly to something. In this case, it's handed off directly to FADH2. Even if you didn't know anything about the citric acid cycle, notice that this is an alpha-beta unsaturated carbonyl compound. So if you remind yourself where you need to get, which is oxaloacetate, you could predict for me what the next 2 steps are. Conjugate addition of water, right, to generate the alcohol. Notice that fumarate is doubly alpha-beta unsaturated. That is, you've got 2 identical beta carbons that are both adjacent to identical carbonyl carbons, or that are both beta to 2 carbonyl carbons. So we'll take fumarate and we'll do conjugate addition of water the beta carbon, one of the two beta carbons. Nature controls the enzyme controls the stereochemistry and the location of the addition. Basically, nature will generate hydroxide in an enzyme active site like this. Then hydroxide will attack this beta carbon from below to generate an intermediate that looks like this. Here's the new hydroxide on the second carbon. Here's the enolate. Again, nature controls the stereochemistry of that addition step, and then we'll protonate that enolate on the negatively charged alpha carbon, and that then gives us this intermediate, or rather this product, 4-carbon product. Again, nature controls the stereochemistry of carbon 2, where the OH group is. This one is called L malate, where L is an old-timey designation for that particular stereochemistry. The enzyme that catalyzes this process is called fumarase, because it's an enzyme that makes fumarate from malate if you go backwards. Okay, questions about that step? That's just conjugate addition. And then in the remaining 50 seconds, we need to do step 10, which is boring. Tell me what step 10 is. What do you think happens? We want to get to oxaloacetate, which means we got to oxidize the OH group. The enzyme is called malate. Guess what it is? I'm writing it as you're guessing. That's not fair. Dehydrogenase. This is going to use NAD+. We're going to generate NADH. The mechanism will be the standard that you would expect. I won't draw it, but you should be able to do it. A base deprotonates the alcohol, electrons kick down, and hydride gets delivered to NAD+. And that takes us right back to where we started, which was oxaloacetate. So next time, we'll move on to chapter 28. I'm also going to summarize the overall yield, and we'll say something about how many times your body actually has to recycle 1 molecule of ATP to keep you alive. All right, have a good Wednesday. See you next time.